cosmology. Today that means we're going to use our rules of general relativity applied to the universe as a whole. And then next week, or that is 2 weeks from now, we're going to look at gravitational waves. It's all the same methodology. Everything that we've learned, we're just going to do today, but with a different metric. So that's the whole idea. Everything that we now know how to do, we're going to do for different metrics, starting today with that of cosmology. What is your understanding of the universe right now?
Sorry, I'm late.
Oh, please go ahead. Come in. What's your understanding of the universe right now? As in the grand scale, that's big and such, but maybe something more specific. What does it do? What does it not do?
It's expanding.
Okay, it's expanding. Sure.
Expanding at an accelerating rate.
Accelerated rate even. Okay, that is very true. Anything else?
It has no real center.
It has no real center. That's beautiful. Yes. Just collecting ideas. Anything more?
It can be modeled as a gas.
Oh, wow. Okay. Yes, it can be modeled as a gas. Where did you pick that up? It's true though. But
From Ronald.
okay, Ronald told you this. Okay.
We can see the entirety of it.
We can or cannot?
Cannot.
We cannot. Why not? Why not that way?
When you see the furthest light.
Yeah, that is true, of course. I mean, it takes light some time to come to your eye, and if the universe is only this many billion years old, then the light can only have traveled this and this far. Yet, the observable universe is bigger than the amount of distance light could have traveled in the age of the universe. Right? The age of the universe is about 13.8 billion years, yet we can look up until about 80 billion light years. So we can see more than light has had time to come. Why would that be?
Because it's expanding.
It's true, but can you be more specific?
Well, if some photons travel to your direction while the universe is expanding, that's how I would present it, but basically they're arriving, like it kind of reduced the distance between us.
Well, that is very true. If I am on my way to you, and in the meantime the universe is expanding, but it's expanding more strongly in the back of me, then I'm already on my way, right? So even though the universe is already bigger, then it means I can still arrive at you, and I did come from that quote-unquote boundary over there, so you are able to see 8 billion light years across, something like that. So yeah, that's the whole idea. So heard some things. Expanding, yes, accelerating fashion. How does that work, by the way? Things expanding in accelerated fashion. So it goes faster and faster. That's sort of opposite to gravity, isn't it? I mean, doesn't gravity want things to be close to each other or pull things back? And maybe if things are not contracting, at the very least, the expansion should be slowing down, right? Because everything tries to get back to each other. So
Dark energy.
Yeah. Dark energy. Yes. The answer, of course, is we don't know.
Yeah.
We know that it does. That this is what it does. And there's many reasons, possible reasons, why it does that way. Some of them are collected in this one big term called dark energy, which is another way of saying there's something going on there, and we know its properties, but we don't know exactly what's going on there. And that's one of the things we will see today. We'll actually do the calculation. So we're going to find, we're going to do general relativity, and we're going to find the equations that tell you how strongly the universe is expanding or contracting, given how much energy is in that universe. And to tie everything together, yes, we're going to use the universe is something like a gas. And you say, well, it's not a very dilute gas, right? I mean, you find about 1 proton per cubic meter. So it's a very, very close vacuum there. But sure, you can still see it as a gas. So what we're just going to do, we're going to take the universe as a gas. We don't specify the gas yet. We just say it's a gas. Then relate it to the metric. Then we have a relationship between the properties of the gas and the metric, and then we get some equations to tell you how, given a certain type of gas, the expansion of the universe works. That's the idea for today. And to give you an introduction, you might have seen this video before. It's one of the many versions of this Powers of 10 universe movie, excuse me, where they say, well, suppose that you start somewhere on Earth. I think they take Venice here. And you just zoom out. And every time that you zoom out, you get 10 times further away, 100 times further away, 1,000 times further away. They take the times 10 in an equal amount of time. Otherwise, it takes an enormous amount of time before you've zoomed out enough, okay? So every time that there is 1 second passed, or maybe it's 2 seconds or something like that, in any given certain amount of time, a factor of 10 outward. This is zooming out that you will get. Well, let's see what we get. Again, I think this is Venice. So this is what, 10 meters away, maybe more. Close to 100, I think, by this time. Here's a circle. Here's not a circle, this is 100 meters. Every time that there's a circle, there's another factor of 10 bigger. So that's 1,000. There you go. At some point you're zooming out. There's Earth. This is no orbit of the moon or such. This is just another circle of 10 times bigger. Here's the moon. So we're at 400,000 kilometers now. So this is 4 million, 40 million, etc. Here are the orbits of the other planets. Zooming out, zooming out. Now the sun has now become a distant dot, and still we're zooming out. Notice how long it takes before you come to the next star. There they are. That's the first star. You have to do a lot of zooming out before you come to the first star. Do you know how far the furthest star is away, or the closest star is, apart from the sun? Do you happen to know the number? Yes, that's the name. Do you know the number, how far away it is? Sorry?
3 or 4 light years or so?
Yeah, it's 4.3 light years. So, well, that's pretty far away. Yeah, you see this by the amount of zooming out. The amount of time that you have to zoom out by a factor of 10 before you find the first star. So 4.3 light years or so. Now we're continuing now. So those are the first stars. Not a factor of 10. And of course, by this time, we will be seeing the galaxy, the Milky Way. There you go. So this is the galaxy. It's about 100,000 light years across. So we're that size now, still zooming out, and you see all these smaller galaxies around us, Megalayan clouds and such. We're zooming out more and more. And at this point, all these small dots that you see zooming, that come into play when you zoom out more, those are galaxies now. Complete galaxies. And in fact, most of the stars that you see at night are indeed galaxies themselves. There was a big discovery at some point because people thought, well, there's just a star, there's another star. Most of them were galaxies, each of containing about 100 billion stars apiece. And at this point in time, we have about 200 billion galaxies that are known. We haven't counted them all, we haven't named them all, there are too many of them, but just by order of magnitude estimation, you can say there's about 200 billion galaxies or so. That order of magnitude, each of which containing 100 billion stars. Now, we zoom out more and more. All of them are galaxies. And then at some point, you will get here. Now, at this point on, the movie will go inward again, go back to Venice, and then go back in with powers of 10, and you will get all these little particles and quarks and protons and such. So that's a nice video to show in a nuclear physics course or so. For us, this is important. This ending picture, this is the observable universe. Does it look like a gas? If you just replace all the dots, all these galaxies by particles. Sorry? Yeah, sure. I mean, it looks gassy, right? I mean, there's some gassiness going on here. I mean, there's some clutter. I mean, there's stuff here, some more here and here than over there. But I mean, in principle, it looks gassy, right? By good approximation. So that's true. As far as the matter distribution is concerned, it looks pretty much like a gas, even though there are some pieces where you find some more. I'll tell you something nice about these condensed parts in a second. Yes?
So, if the universe is infinite, where is this picture taken from? Because there is no edges to the universe.
Yes, but I don't understand why there's a question there. If you zoom out, you can always point your camera back and take a picture, yes?
Yes, but you need to go to the edge of something to be able to take such a picture.
Who says it's the edge?
You could be in the center or just.
Yeah.
Suppose that you're standing in a desert and you're just walking outwards. At any point, you can turn around and take a picture of the desert before you, right, where you just came from. You don't have to stand at the edge of the desert to take a picture of the inside of the desert.
Yeah, okay.
Well, yeah, it looks pretty gassy. I promise you to say something nice about these parts where things are more condensed. Or maybe you already know why that is. Do you have some idea? It is pretty strange. Why would there be more of this stuff here than, say, here? What is so special about this place? or that place.
Maybe because for some reason there was a bigger amount of matter in the first place.
Yes,
and
that is
then
yes.
gravitational pull started to.
That is very correct. I mean, you have some runaway effect there. If for some statistical reason you have more mass at this point, a slightly small amount more mass, then you also have more gravitation, which will attract more mass. So you have a bigger amount of mass, which will make more gravitation, which will attract more mass, and you'll get this clump of mass. That is very true. But then, of course, the question is, why would you have more starting mass at that particular point? Is that just random statistical fluctuations, or sure, why not? I mean, if you have a gas, you would expect, I guess, a vessel of gas or something like that, some container. You have more gas particles here than over there.
I mean, or some quantum effects so that they would wiggle on a small scale.
Oh, that is very interesting, because you're talking about two effects now. There's statistical effects, as in you have all these bouncing particles, so there is a probability that there's going to be a little bit more mass here than there. That's statistical, just because this is because of entropy as such. Now, if you look at a barrel of gas and you put these gas particles in, you'll be very hard pressed to find parts where you have a clutter of mass more than over there. It means it's statistically almost impossible. This is the basics behind the second law of thermodynamics. But there is, of course, quantum fluctuations.
Like tunneling and stuff.
Sorry?
No, like tunneling, the absurdity of location and stuff. like that.
Exactly, yes. But then again, quantum effects only occur on very small scales and not on universal scales, right?
These quantum fluctuations, they occurred at the beginning of the universe, didn't
Yes.
they? And the effects of the quantum fluctuations back then are still visible now.
Yes, exactly. At the beginning of the universe, where things were smaller, that you would see quantum effects. Yes, you would have, just by Heisenberg alone, you would have places where there's more mass. Not because of bouncing particles or thermodynamical statistical fluctuations, just because of uncertainty by Heisenberg. You have places where there happen to be more mass. But they're on an extremely small scale. So you have a sort of clump of matter maybe at a small scale, but then it expands, because the universe has been expanding. So that means that all these quantum mechanical fluctuations at the beginning of the universe have also expanded. And this is indeed why you have all these clumps here and there. So literally, if you look up with your telescope and you see these things, you're really looking at quantum mechanics on a universal scale. So you have these people who walk around and say, well, quantum mechanics only operates on small scales. Well, that's very true, but it's visible on big scales. And this is one prime example of that. So whenever you look outside and you see things being clumped together, universe, you say, oh look, there are some quantum fluctuations there. Now you might have seen this picture too. This is the Planck picture. It was a very big thing. There were, well, a number of experiments, but the most important ones I think would be Kobe in the 90s and WMAP early 2000s, and then Planck. They all measured the same thing. What we just saw on the previous picture was how matter is distributed. But you can also look how energy is distributed, and by energy I now mean the photons. And if you take a picture of the microwave background radiation, the ambient light in the universe, you will get this picture. Now, of course, they're not real colors. They exaggerated it a lot. So you have these warm spots, you have the cold spots, and I think that the colors are inverse or something like that. This might be the warm spots and this is the cold spots, but it's beside the point. The point is that if you look here, then energy seems pretty evenly distributed as well. This is a picture of the whole of the universe, as far as we can see. And you just look around and you see, well, are there warmer photons coming from that direction or from that direction? You see, well, it doesn't really matter. Wherever you look, it looks pretty much the same as far as the energy is concerned. Well, you might say, well, but I do see some differences, because this is very blue and this is very red. So one of the pieces is there's more energetic photons than the others. Yeah, but the differences are about 10 to the power minus 5. So that's about 1,000% difference between the two parts. So don't get mistaken by the different colors. It might give you the impression that there's a huge difference in temperature. No, it's pretty much the same everywhere, up to 5 digits. So we have two very strong indications that as far as energy and matter is concerned, the universe looks pretty much the same everywhere, doesn't it? Now, again, 3 experiments that measured this. One Nobel Prize went to this. It was in 2006, if memory serves. Yeah, 2006. For the measurement of this thing for the first time. Because there's an enormous amount of information in here. We don't get to go into all of it, but this picture and its predecessors gave us an enormous amount of information about the early universe. Now for us, the only thing that is really important is look at how evenly distributed energy is over the universe, and then the previous picture, how evenly distributed mass is over the universe. Now, that's the whole idea, because that is going to be our starting point. Yes. Because now, let's continue back to the board. This idea is called the cosmological principle. That's the starting point of relativistic cosmology. Cosmological and the idea of the cosmological principle is twofold. First of all, it's exactly what I just stated before. If you stand someplace and you look in all directions, no matter where you look, the universe will look pretty much the same. That was that picture that we saw before. From a certain position, in our measurements, of course, that will be the Earth. The universe, and by this mean its matter distribution and its energy distribution, looks the same. The universe looks the same in all directions. And the official word for this is isotropy. The universe is isotropic. It's just another way of saying it looks the same everywhere, in every direction. Now this you can just measure. This is what we have measured. We've seen this, as far as we can tell, holds true. But a purist could come by and say, well, maybe it only looks the same in all directions as seen from Earth. Maybe if you would have stood someplace else in the universe and then would have done a full 360, it would have looked different from different positions. Now this we cannot measure right now. We cannot go to another galaxy and then do the measurement again. So it's an assumption that this isotropy holds everywhere. That no matter where you do your 360 search of the universe, we will get the same answer. So a second part of this is, and again this is experiment, this is assumption. The second part is that this statement holds for any position in the universe. So no matter where you stand and you look around, it will look the same.
This is just a claim, or?
Well, it's an assumption. Yeah. Again, we cannot really check this. Not in any direct way, because that means that we have to go travel 15 million light years to go someplace else and then do another sweep of the photons. And it's just practically impossible. But you can put some philosophy into play here and say, well, suppose that it's not true, and it's really the Earth, the only place in the universe where everything will look the same. That would be a very big coincidence, unless maybe you have some philosophical reason why you think that, of course, naturally it should be the Earth. But speaking from a scientific point of view, saying, well, you have this planet here randomly, and it just happened to be that everything there was such that life could evolve, and there was intelligent at some point. They could do measurements. What a big coincidence would that be if that particular planet happened to be also the exact same planet where everything looks the same? Unless there is some correlation that we're unknown, that we're not familiar with. This is called homogeneity. Now, to make the distinction between the two statements a little bit more clear, if you go and stand in the bullseye of a dartboard or so, and forget about the different numbers that you see with this is 20 points, that's 10 points, and so forget about the numbers, just the way that it looks from the bullseye of a dartboard. If you look around, in every direction, the dartboard will look pretty much the same. Your view will be somewhat the same, yes? But if you would take 2 steps to the side of the dartboard and you then do your 360 sweep, it will look different, because there's a bullseye, and behind you there isn't. So a dartboard would be isotropic if you stand in the center, would not be homogeneous. Then again, let's take the desert again. let's make it big enough. If you go and stand over here and do your 360 sweep, you see a couple of cacti maybe, and maybe some desert snake and lots of sand. And you would see the same thing if you would stand 10 kilometers away and do the sweep. So that would be homogeneous and isotropic. So the cosmological principle is both. And the way that people typically phrase it is as follows. The universe is isotropic and homogeneous in its energy content. And by energy I now also mean mass, so mass and energy. But of course this only holds if you look at a big enough scale. Right? Very locally I can say, well, there's the sun and over there isn't. And there are some planets over there and over there isn't. So it only holds if you zoom out enough that all the galaxies and stars have become dots, that final picture. And the typical scale that people use, how much do you have to zoom out? The typical scale that people take is about 100 megaparsecs, 100 million parsec. And a parsec is about 3 point something light years. It's an astronomical unit. So in the order of magnitude of a couple of 100 light years, at this point, when all the galaxies look like little dots to you, at this point everything will have a very homogeneous and isotropic distribution. So this is cosmology, this is the starting point. And of course the question is, how do we put this into mathematics? Knowing how general relativity works. Question, why would we assume that we need general relativity to explain all this? Why not one of the other forces, or quantum mechanics or so, or something like that? I mean, general relativity is only one of the physics theories, right?
Is it just because this study involves big masses and such things?
Well, that is certainly true. I mean, whenever you have big masses, you expect gravity to play a role, but you also know that forces like electromagnetism is much, much stronger than gravity. And the strong nuclear force is as well, and even the weak nuclear force is. Yet of all these four forces, we take gravity to be the driving force behind everything in the universe. Why not one of the others?
The distances are so long, like the only force really acting on anything is gravity.
Well, that is very true for the weak nuclear force, because that only has a range, well, only has a small range. By the way, the same for the strong nuclear force, which only has a range of about the size of a proton. So at this scale, strong nuclear force certainly is stronger, but it plays no role whatsoever. It only plays a role when you try to squeeze quarks together and such. So these two are not there. Electromagnetism.
Well, it decreases with bridges as well, right?
Would decrease how?
I think it's exponentially, but not sure.
It's no, it goes 1 over r squared. Electromagnetism. But then again, so does gravity. Coulomb's law that says something about how strongly two charges are attracting each other is the product of their charges divided by their relative distance squared. But gravity, at least in Newtonian, is the same thing. It's the masses multiplied with each other divided by r squared. So they both drop down with the same rate. Yet of these two, we take gravity to be the one and not electromagnetism. Well, we're good about these strong and weak nuclear forces. But of the two remaining ones, why do we take gravity?
Does this have something to do with the fact that the universe is overall neutrally charged?
Yes. Things are typically neutrally charged. So that means, yes, given if you had a proton here and an electron at the other side of the universe, they would feel an attraction. The fact is you don't have protons here and electrons over there. And that this is an exact direct result of the fact that the electromagnetic force is very strong. It's very hard to get protons and other charged particles to let go of each other. And at the moment that you have let them go of each other, the electromagnetic force will suck them back in. And gravity does the same thing, but not as strongly. Not quite. The gravitational force are extremely weak. This is why you need universe to see them in the first place. And because of that same reason, let's put it differently, because of electromagnetism's much stronger attraction between charged particles, it's very hard to get an electrically charged universe. The first thing that the electromagnetic force wants to do is make everything neutral. Now, if it has succeeded in such, well, the only thing that remains is gravity. It's really just because it's the only force that operates at this big scale and is not neutralized. The second thing is you cannot neutralize gravity because masses only come in one variety, plus. So there's always going to be attraction. So there's no neutralizing in the first place. So we know that we have to put our understanding of what the universe looks like into gravity. And that, of course, means general relativity in our case. Now, what I propose to do is we're going to take this cosmological principle and do two things with it. First, we're going to guess what the metric is going to look like, just based on this. And secondly, we're going to guess what the energy distribution is going to look like. And then combine these things together. So this will lead us to two things. As a result of the cosmological principle, there's a statement about the metric. Will be such and such and such, and there is going to be a statement about the energy distribution. And it's up to us to decide what is going to be the content of these two statements. Let's start with the energy distribution first. The universe looks the same everywhere. And you would have to model the energy in the universe. What would you use? Think of something else that looks the same everywhere.
Like a sphere or something.
Sorry?
Sphere, something spherical.
Oh, we're going to use that instance for a metric in a second. Can you name something tangible, something that you can actually physically touch and measure? That is the same everywhere? I'm looking at you because you already gave the answer before.
Yeah, a gas or a plasma or something.
Yeah,
like
exactly.
that.
Yeah, I guess. I mean, if you have a vessel of gas or container of gas, and you don't pay too much attention to the statistical fluctuation because of thermodynamics, then the pressure here is going to be the pressure there, and the temperature here is going to be the pressure there, a gas equilibrium. So people say, well, you know what? If we know from experiment, cosmological principle, that the energy distribution has to be such that it is the same everywhere, that means we can just describe the universe's content, energy content, as a gas. You can just borrow your thermodynamics, all these rules, and use that. So yes, that's the idea. The universe's energy content we will model as a gas. Question. Does it have to be an ideal gas? You remember what an ideal gas is, right? What is what there are two properties of an ideal gas.
Was it like 6 or something?
Yeah, I think it was like 6.
Oh yeah? Okay, tell me what the 6 are.
This property
pressure,
that
something with temperature.
Pressure was something like 1 atmosphere.
the pressure times the volume is a constant. So pressure times the volume.
Oh, in the ideal gas one.
And RT.
That one. Oh, and that may be split up in Gay-Lussac and Boyle's law, which are two separate laws that combine together to make the ideal gas law. Okay, sure. That is fine. Okay, anything else? So there's at least 2 of these statements into one, right? It's the pressure times the volume of the gas equals the amount of moles of particles in there, times some constant, 8.5 or so, times the temperature in kelvins. That's true. Anything else? Properties of an ideal gas? Doesn't necessarily have to be formulas, by the way. It could also just be statements.
In an ideal gas, would the atoms and molecules like not
Yes.
interact with each other?
Exactly. So this is highly hypothetical. They only interact with the surroundings, the thing containing the ideal gas. So they don't bounce into each other, they only bounce into the walls of the vessel. Highly hypothetical, of course. That's very true. So the particles do not have interaction with each other. You can see them as free particles apiece. That is very true. Let me give you another one. The temperature of an ideal gas is the only thing that you need to calculate what its energy is. This is certainly not the case for all gases or all other mixtures or so. Typically, if you give me a barrel of gas, one substance or another, and you ask me what its energy content is, its internal energy, I typically need a couple of numbers. I need both the pressure, I might need the volume, and I might need the temperature. Ideal gas is the one exception where you only need one of these numbers to calculate all of the rest, which is the temperature. So that the internal energy, which you typically call U in thermodynamics, is only T dependent. Now, and there's of course all kinds of other properties that come with this, that you might know or might not know. Not very important right now. By the way, as a fun exercise, what you can prove for yourself is that if you assume that the law of conservation of energy holds, first law of thermodynamics, which is this one, the change in energy is equal to minus the pressure times the change in volume plus temperature times the change in entropy. This is first law of thermodynamics. And you assume that this is true, you put that in, then this will pop out. It's a fun mathematical exercise. So just for funsies, if you just assume that energy cannot be created or destroyed and that there exists a thing called entropy, then you find that there's really only one particular situation in which things only depend on the temperature, where energy only depends, excuse me, I'm saying this correctly, but I'm getting tongue-tied in my words here. One step back. If you assume that entropy exists and that there is a law of conservation of energy, and you put in this, you will get back the ideal gas law, which is another way of saying that even if you don't specify what exactly is happening within the gas, bouncing particles or such, the only thing you have to assume is that the energy only depends on temperature, then it will always obey the ideal gas law, even if it's not a gas. So this law is more broad than just for gases. Now, if you look up in that thermodynamics book where they get this law, they either say it's because of experiment, Boyle and Gay-Lussac in the 1700s or so, 1600s. There's also some derivation where they say, well, you have these particles and they bounce into each other, and if you then do the statistics on the ensemble, you will get this law, which is all very true. What I'm saying is, even if you take out particles whatsoever, you also get out this law. So it's a very deep law. It doesn't just apply to gases. It applies to everything for which the temperature only depends on, the energy only depends on temperature. Long story short, we don't have to assume, in our case, that the universe is an ideal gas, but it is a good approximation. Okay, so that's one. Universe energy content we will model as a gas. Could be an ideal gas, doesn't necessarily have to be so. How about the metric? This is fine. We have put our cosmological principle into an assumption on how the energy distribution will be. How about the metric? Given that we take this as fact, is there any statements we can make about the metric?
Spherical.
Explain that.
Well, it has like an even distribution everywhere, radially. So
That's a very good statement. I mean, one thing that looks the same wherever you stand, in every direction, is a circle, right? If you have this this beach ball, and not the one with all kinds of colors, but this white beach ball, no matter where you stand on the beach ball, in every direction, it will look the same. And will also be if you step on some other point of that beach ball.
But then if you were inside the beach ball and you would move a bit to the left or to the right, imagining that you would be in the center in the beginning,
Yes.
then you wouldn't see the same symmetry as in the beginning.
Yes.
Because you would be shifted away
But if
from
you
the
make
center.
it large enough.
No, but no. There's a slight misunderstanding here. When I say that the universe is spherical, or it's his statement really, but if you say the universe is spherical, what we don't mean is that there is a spherical thing and you happen to be in the middle of the thing. What I'm saying is you're on the surface of the spherical thing and you're only allowed to move over there. On that surface, where no matter where you stand, as long as you stay on the surface, it will look the same everywhere. Agreed?
So you say that the universe is like a giant ball?
Yes, but it's a hypothetical ball, or it's called hypersphere, where our beach ball in my story here is itself two-dimensional, right? Now imagine that you have a situation, it's hard to envision that visually, but mathematically you can easily write this down. Imagine that you have a situation where you have a beach ball of which the surface is three-dimensional. Yeah, that's hard to visualize, isn't it?
So you have like a three-dimensional axis system sitting on the surface on top. So you could go inside or on top of the surface.
No. And we have to get this misunderstanding out as quickly as we can. Here's a sphere. And you stand over here on this little patch here. And if you look around you, you will see certain surroundings, yes? And if you go and stand over here and you look around, you will see exactly the same surroundings as you would over here. That's the cosmological principle. Now this sphere is itself three-dimensional, but the surface of the sphere is two-dimensional. Agreed? Okay. Suppose that we restrict ourselves to only moving on the sphere, then this is not a good description of the universe. Because that says, well, we're only allowed to move in 2 dimensions, and we know that the universe, spatially, you are allowed to move in 3 dimensions. So what we could envision, it's hard to do this visually, but you can write down the mathematics for this and say, well, suppose that it's not a 3-dimensional sphere with a 2-dimensional surface. We take a 4-dimensional sphere, of which the surface is then necessarily 3-dimensional, and it's on the 3-dimensional surface of a 4-dimensional sphere that the universe lives. It's ridiculously hard to make a mental picture of this.
Is it so possible?
Sorry?
So possible to make
Maybe it's even impossible. There are people who claim that they can.
Can you?
Well, I can write down the mathematics and
Yeah, but visualize it.
My claim is that if you practice mathematics long enough, at some point you will get some intuition just by getting used to stuff, right? I mean, when I was 15, I had a very little understanding of what an integral was, and I have no difficulty in having intuition. So when we give him an integral, and I feel, well, it's sort of like this-ish. So my contention is more psychology than physics here, but my claim here is that if you do something long enough, at some point you'll get used to the thing and you will get some sort of physical intuition for the thing. So no, I don't know how to visualize a 4-dimensional sphere on which there is a 3-dimensional surface, but I've done the mathematics so often that I have no difficulty thinking in those terms. Anyway, this is what we have to do, because we are looking for something in which you can move in 3 directions and it will still look the same everywhere. So again, this is not a 3-dimensional sphere, 2-dimensional surface, but you're allowed to move in the 3rd dimension radially inward or outward. No. We're going to have a 4-dimensional sphere and our universe on the 3-dimensional surface of that thing. Hard to visualize, we can write down the mathematics.
But so, would we be able to go inside the sphere?
No, because we only live on 3 dimensions.
Oh, okay. So there's no way we could ever conceptualize.
No, but you don't. I think you have to. You don't have to take these 4-dimensional hypersphere too seriously, as if there's really, literally, in a 4-dimensional sphere living in the universe. The only thing that we're looking for is some mathematical description that obeys the cosmological principle. I'm not saying that there's literally a 4-dimensional sphere that we live on a 3-dimensional surface. I'm just saying it looks as if, and that's good enough for our mathematics. Yes.
So why would you make this surface 3-dimensional, not 4-dimensional? Since we can actually also move time.
Because that's a very good question. In fact, the cosmological principle is only a statement about that it looks the same in all spatial directions.
Okay.
It does not say if you move in time it will look the same. In fact, we very well know that it's not true, because if you go back in time and then do a sweep around, then you will see that the universe does look very different. That thing has existed at some point in the theory of relativity and cosmology about 50 years ago or so. It was called the perfect cosmological principle, where this not only holds in space but also in time. The universe has looked the same isotropically homogeneously at any moment in time even. Now if you take that into account and you do the mathematics, you will find that the only way that holds is if you have spontaneous creation of matter and energy from nothing. That's the only way that this will work if you do the mathematics. So people abandoned it, and then of course later on came the measurements that really said, no, it really did look different in the past. Now, if for some reason you do want to go back to the idea of that even in time it should look the same everywhere, then that means that you would have to have a 5-dimensional sphere on which there's a 4-dimensional surface, one of them being the time direction.
Yeah.
But experiment has discredited that idea, the perfect cosmological principle, so it doesn't exist anymore. Yes?
When you were talking about the universe looking different before and whatnot, but wasn't it still isotropic and homogeneous
Yes.
during the Big Bang and all that? So why couldn't you just have a principle? Okay, never mind, I answered my own question.
I think so. Okay. Just to drive it home just a little bit more, the statement, the cosmological principle, to put it in practical statement, is if you were standing over here, and I would close your eyes or subdue you for an amount of time, I transport you over here, then you open your eyes. Could you tell from your surroundings that I moved you from here to there? And the answer is no, in the cosmological principle. If, however, I subdue you and transport you back 5 billion years in time, and then you open your eyes, you can immediately tell, wait a minute, I've moved in time because things are much closer to each other and such. That is the key difference. But okay, but here's an option. We were looking for something that looks the same spatially, and one option, don't take it too seriously, as in there's no real 4-dimensional sphere with a 3-dimensional surface, but it looks mathematically as if there is. So that's one option. Write down a metric that describes a 3-dimensional surface of a 4-dimensional sphere. And that will agree with this. That's not the only option though. Can you think of any more? There's 3 of them. One of them is the spherical universe, and again spherical in the sense that I described. Can you think of something else? A curvature that looks the same everywhere in every direction. Flat. If the universe is a flat space, a flat space looks the same everywhere in every direction. Again, I have to say here now, what I mean by flat is not that the universe is some big sheet of paper that floats through a bigger universe or something like that. I mean flat in 3 dimensions.
Oh my god. Flat in 3 dimensions sounds so iffy.
Yeah, it's not iffy. No. Let's put it in practical terms again. One key element of a flat space, piece of paper, is if you would draw 2 lines, they would not close in on each other. Now what if I present you with a universe where 2 lines, even if they start parallel and nothing is moving on or acting on them, they will still find each other at some point. You know that you're not in a flat universe anymore. But suppose that that trick works not just in this direction, but also in that direction, and in that direction. In that sense, it's flat. Now, of course, it's hard to envision a 3-dimensional flat surface. But in practical terms, it means any 2 lines, or if you will, any 2 solutions to the geodesic equations, will not cross each other no matter in what direction you try. And there's 3 directions to try.
Wouldn't them basically just be a cube though? Because you have all the faces where you just draw the lines.
A cube with
Yeah,
no edges.
yeah, there will be a 4-dimensional cube. Because the surface has to be 3-dimensional, it should be a 4-dimensional cube. No edges, because you're not allowed to pop over an edge here and there. So it's a 4-dimensional infinite cube on which we live on the 3-dimensional surface.
Yeah, because we're still
Yes.
on the surface then.
Yes, always on the surface.
How do you know a 4-dimensional cube is not going to have edges?
Again, we just need the mathematics. Don't take the actual physical picture, the actual visual picture of this too seriously.
Yeah, I'm just curious.
So that's what we call flat universe. Oh, by the way, the 2 lines, and that as a practical definition of how curved your space-time is, them finding each other at some point, that will define a spherical surface. And the fact that it's 3-dimensional spherical universe means that if you have the 2 lines going in that direction, they would find each other at some point, and if they go in that direction, they would find each other, and if they go in that direction, find each other. So in all 3 directions, any 2 lines will cross at some point. That's what we call spherical. Final option, maybe. Yes.
I think I read somewhere at some point about it was like a donut-shaped universe.
I was just thinking about that as
A
well.
donut-shaped universe
Yes.
with a hole in it and such. And
Yeah,
Okay.
that shape. I don't remember exactly how they described it, but yeah.
Yeah, I
That's-
have no idea
that's-
why.
that's
I have
my
the same
thing.
hunch as him also.
well, I will give you the name first. It's called the hyperbolic universe. And this one I find really hard to make a mental picture of, because I sort of understand a beach ball and lines going to each other and such, because I know how globes work, but this is more difficult. But you can already see where this is going, right? Because this one is the option: any two lines will never cross, whatever direction you start them out. This is the option: you have two lines at some point that will close in on each other, no matter in what direction you try this. So what would this be?
All lines would drift apart.
Yes, no matter in what direction. That's also an option.
Could be like being in the center of a sphere.
Yes.
Right?
That is exactly it. It's as if you live on the inside of a sphere and look at the boundary and see what happens over there. Because if you would start at the North Pole, you would draw two lines that would be moved away from each other. This is called a hyperbolic universe. It's the inverse of a spherical universe. Now I hope for all of these you will see that no matter where you stand on that three-dimensional space, on a four-dimensional, hard-to-envision thing, it will look the same everywhere, isotropic, right, in every direction, and this holds true at any position in that space. These are the only three options. You can think for yourself if there's any more. The answer is no, not in three-dimensional space. And the people who did the first research on this were called, well, there was a number of people, but they're typically named after these two, Robertson and Walker. There's some other names that you typically see here is Lemaitre. And who's the other guy? Friedman, etc. So these universes are typically called Robertson, Walker, Lemaitre, Friedman universes. And the corresponding metric is typically called the Robertson Walker metric.
It sucks for those last two.
Sorry?
It sucks for those last two guys
Why is that?
because they don't have the metric.
Oh, well, yeah, but Friedman has a number of other things named after him, so we will see them later on today. These are called the Robertson Walker metrics. And as you can see, there's three of them now, okay? There you go. So here's the idea. We have a proposition of three possible metrics that obey the cosmological principle, and we also have a proposition how the energy is distributed based on the cosmological principle. So we have a metric. We'll save the mathematics for the next half. We have the metric, and you have the energy distribution. And at this point, you have to combine these things together. And all this time we've been talking about curved space-times. I never told you where the curvature came from. We just named it. There is an equation that connects these things together. These are the famous Einstein field equations. I wrote them down before. Here they are. Depending on which author you happen to be reading the articles or books of, there could be a minus or a plus sign. There's no physics there, it's just convention. I was brought up by this book, the Gravitation and Cosmology by Weinberg, which has the minus sign, so I'm always using the minus sign. But don't worry if you find it with a plus sign somewhere, it's the same physics. The idea is that this thing is a tensor that tells you what the energy distribution is, how much energy is there at what point in space. This whole thing is just one big combination of the metric with itself. It's a ridiculously complicated expression. This is why it's abbreviated in this form. Because this R over here, it's called the Ricci tensor, is itself a particular combination of derivatives of the Christoffel symbols. And the Christoffel symbols were derivatives of the metric. So this thing really is some weird combination of second derivatives of the metric. My point here is you only need the metric to determine uniquely what the Ricci tensor is. Now you have this other R here, it's called the Riemann scalar, and that is if you take the Ricci tensor and make a contraction with the metric itself again. So that's some strange combination of second derivatives of the metric in a contraction with the metric.
What was it called again?
The Riemann scalar. And this is called the Ricci tensor. We're not going to do too much with these things in detail. Ricci tensor. And I promised you all this time that I would say something about the Einstein field equations, and now's the time, because I want to give you an argument why this is the right equation that connects energy to curvature. Now, one thing that you already know is you need energy, this tensor, to make space-time curves in the first place. Right? It's curvature, or it's energy and matter that makes gravity, and gravity in general relativity is curvature, so that these things are related to each other should now be physically obvious to you. But why is it this particular combination? And that was Einstein's question. He knew that there should be some connection of this thing and something with the metric tensor. And the big question was, what is the exact combination that relates this to this? And it took him a long time, like 7 or 8 years or so, to find out what the particular combination was. He ultimately found that it was that combination. And the way that he did it really was this. There's a theorem in curved space-time mathematics, and it says that a tensor you can always write as a Ricci tensor plus a constant times the metric times the Riemann scalar. This is just a mathematical theorem. That any tensor you can write in this way. It's not completely true what I'm saying now. There is one small caveat, and that is if you assume that the curvature of space-time can only be up to second derivatives in your metric. So that there's no higher derivatives than the second in this expression here. And Einstein, for physical reasons, thought, well, whatever the curvature is, it should appear in this connection with the energy only by second derivatives. No third derivatives, no first derivatives, only second derivatives. Now, before we go into why that is, given that that is the case, that you can only have second derivatives of the metric on this side, then this mathematical theorem tells you that you can always write it as this thing plus constant times this thing. And then it was only up to Einstein to find what this constant should be. And the way that he found it was by saying, well, I know that if I look at things that are not too gravitational, I should get back a version of Newton's laws. And that was enough to fix that it should be minus 1/2. And this is how I got the rest. Well, this was a 7-year quest in 2 minutes or so. Can somebody think of a reason why there should only be second derivatives here? This is a very difficult question, but maybe you can have some feeling why that is. Why no third derivatives? Why no four? Why no first?
Maybe it related to Newton's second law.
Because there's second derivatives there? I think there's something there, yes.
Because we saw before how they, like, forces related to...
Yes.
I'm not exactly remember the word.
Inertial frames, non-inertial frames?
Yeah, non-inertial frames.
Yes.
We saw, yeah.
No, you're on the right path. Yes. Let's deal with the first derivatives first. Okay, why there's no first derivatives? First derivative, right? If the left-hand side is allowed to have first derivatives in there, that will mean that you can do away with all fictitious forces. If you go back to Newton's mechanics, you found that if you are in an inertial frame, you can easily go to a non-inertial frame by going with constant velocity. That's one derivative. But the moment that you get fictitious forces, gravity is the moment that you have two derivatives. It's the moment that you put in acceleration. So it's a second acceleration, a second derivative effect that should give you gravity. So you knew it has to be something with no first derivatives, because first derivatives you can easily do away with going to another inertial system, while we have to deal with non-inertial systems, and those only appear in second derivatives. Now, why no third derivatives or fourth? That is just well, we sort of touched upon this last Thursday. remember that we were doing this Schwarzschild thing that we said is gm over r c squared, because that thing is unitless, and that's the only thing you can subtract from a Minkowski metric. And then I said, well, it's a very small number. I forget what it was, 10 to the power minus 23 or something like that, some small number. Now, if you want to add third derivatives, which is also allowed, or fourth, it's allowed for the same reason that second derivatives are allowed, because then you introduce accelerations. But the third derivatives come with an extra factor of gm over c squared, which makes an extremely small number. So even if there are more terms in here, higher derivatives, those come with their own gm over r over c squared, which become extremely small numbers. So Einstein just threw them out. He said, well, they might be there, they might not be there. But as far as all practical matters is concerned, these are such small numbers, 10 to the power minus 23 squared. It's so small, so far behind the common decimal place at some point, this is thrown out. Now, given that that is the case, under the assumption that there should be only only second derivatives here of the metric, then this mathematical theorem tells you, again, then it's some combination of these things that will describe all of your curved space-time to you. And it's connection with Newton that fixed the 1/2. And this is how he got there. Okay. Now at this moment, this is the part where, what was this phrase again? Curvature tells matter how to move, and matter tells space how to curve. This is the space how to curve part. We have always assumed now that we already know what the answer is. Now we're going to do something else. We're going to say, well, we're going to take the Robertson-Walker metric. So we're going to assume that we already know the form of the metric. We already know g mu nu, or g alpha beta. Calculate this whole damn thing, which is just a combination of that particular difficult thing. And then relate it to the T mu nu that corresponds to an ideal gas, or non-ideal gas, to a gas. If you then work through this mathematics, what will pop out is an equation that relates the properties of the gas to the curvature of space-time. In fact, two equations will come out. And they're called the Friedmann equations. I promised Friedmann would make another appearance. They're called the Friedmann equations. At that moment on, cosmology is going to be quote-unquote simple, because from that moment on you don't have to worry about these things anymore. Just what you do is somebody tells you how much energy there is in this gas. Somebody else has to tell you how much pressure there is in the gas. You put it into these Friedmann equations, you solve the Friedmann equations, and you know how space-time, its curvature, will evolve through time. That's the idea. Now, I promised to first go through the conceptual understanding of this before we do the mathematics. So is there any questions about the program or the concepts?
Can you repeat the last process where we first know the tensor,
Yes.
and then we see how that affects the
Okay.
And I mean, you said that we should model the universe as a gas.
Yes.
If we know the tensor, then how
Yes.
do we get the Friedmann equation?
Here it is. So this thing you can write as a tensor. At the moment that you know, or that you assume that you can describe the universe as a gas, you can write down what its g mu nu is. We're not going to go through that step. It's a little bit mathematically involved. You need Lagrange mechanics and such. So let's assume that we know how to do this. Then this thing will give you that.
Oh. Okay.
And
That's the other way around.
this thing will give you that. And then what will pop out is the relationship between this metric and the properties of the gas. So we're using the cosmological principle in two ways now. One, to say something about the right-hand side of the Einstein field equation, and we use the cosmological principle to say something about the left-hand side. And then we combine them together and see what happens. Yes?
Quick. What's the thing next to the pi? Is that a delta or an S?
It's a G,
Small g.
big G.
Oh, left side.
Oh, sorry.
No, still next to pi. 8.
8, yes, that's an 8.
Number 8.
Yes.
Oh.
8 pi g over c to the power 4. That's a small number, but it's 10 to the power minus 45 or so. So it takes an enormous amount of mass before you curve the universe. That's what it says. Right? Because you have to compensate by this number, you have to compensate the smallness of this number. So you need an enormous amount of mass before you finally see some curvature. This is why you need galaxies before you see something happening on gravity scales. Okay, tell me, what are the properties, what are the observables of a gas? Given that the gas is homogeneous, that it looks the same everywhere.
Temperature.
Temperature, sure.
Pressure.
Pressure.
Volume.
Volume, okay. Anything else?
Number of
Number of particles, yeah, sure. Number of moles or something like that, yeah. Now, and depending on what the gas is, there might be more. Now, we're going to look at hydrostatic gases. And that's just a very difficult term to say. That's a gas that only depends on, indeed, these numbers, these three. But it's really two numbers, because numbers are related to each other via something that is called in thermodynamics an equation of state. We already wrote one of them down, the ideal gas. If you have two of these numbers, you can find out what the last one is. These are not separate numbers, independent numbers. They depend on each other. So typically you only have two of these numbers that describe the universe. And what people use in cosmology is that they bring this back to two numbers. One of them is called rho. It's the energy density. How much energy per cubic meter? Energy per volume. And they take the pressure, as if you would put the whole universe in a barrel and see how much it is pressing against the sides. We're now simplifying matters because, of course, a real gas might have more numbers to describe it, but it's typically good enough. In fact, you can already see this from your thermodynamics, your ideal gas. Suppose that we have an ideal gas, then energy per volume for an ideal gas, energy is completely fixed by the temperature. That was one of the properties of an ideal gas. And then you divide it by this number, you will get this number. So this rho already encapsulates these two. This one is just that number. You don't have to make the assumption of an ideal gas. In fact, you can make it much more complicated. You get into something that is called thermodynamic cosmology, that you actually put in temperature effects, and then makes life much more difficult. In fact, this is what I did my master's thesis on. I can tell you from personal experience, it makes life extremely complicated if you put temperature in, because then you have all these entropy fluctuation effects that otherwise you would not have. Now, we're not going to go as far as this. Just going to say that this thing will be pressure and density dependent. So this takes care of the whole right-hand side. Left-hand side. Robertson-Walker metric. You tell me, what does it depend on?
The mass distribution of the universe?
No, because that's already in here. It's related by the Einstein field equations, that's very true. But just itself, the three-dimensional sphere, space on a four-dimensional sphere and such.
Space and time.
Well, that is very true.
It depends on which of those three options.
Yes, that is very true. There's a number in there that's called K. And it tells you which of these three options you're looking at. I already fixed that for you. It's a dimensionless number. It's called the curvature factor. And it comes with the number +1. That's a spherical possibility. It comes with this number 0, that's flat. And it comes with the value -1, that's the hyperbolic possibility. Why +1 and not +4? That's just a matter of convention. Yes?
This has nothing to do with the expansion, like if it's going to expand more, stay static, or contract again.
Well, it does actually, but in a way that I haven't specified yet. The way that I introduce this now, which of the possible three Robertson-Walker metrics there is, just says whether two lines in a universe will cross each other at some point, in which it is spherical, +1. Either they stay parallel, in that case it's 0, it's a flat universe, or they diverge. then it's a hyperbolic universe, k is -1. But we will see when we have the Friedman equations that this is directly related to if the universe will contract at some point. And I will show you that explicitly. So it is related ultimately to what the universe will do in time. But this is not how I introduce it. Back to my question, what numbers do we need? Think of the sphere maybe. You have this 4-dimensional sphere on which there's a 3-dimensional surface. Name me a property of a sphere.
Radius.
The radius. It's a hypothetical radius, if you will, okay? That thing is something that after the break I will put in mathematical terms, is what we will call the scale factor. And they call this A. And again, after the break I will tell you exactly what that is. But maybe to give you already some insights, if you make the sphere bigger, the 4-dimensional sphere on which a 3-dimensional universe lives, you make that sphere bigger, what will happen to distances within the 3-dimensional surface?
They will be stretched out.
Yes. That's true.
It would look more like a flat space, right?
That is also true. If you blow up a sphere enough, it will look flat locally. That is very true. But take any 2 dots on an increasing sphere, and you blow up the sphere. The 2 dots will lie further and further apart from each other, right? That's a scale factor.
But they will have to be quite bigger.
Yes and no. You are right, but that effect is very small, in a way that I hope I will get to explain to you later. It's because of Hubble's law, which follows from everything here. To give a very short answer, how about the dots on the sphere itself? Don't they increase as the universe expands? Where you have 2 dots, mean that these 2 will lie further and further apart. That is very clear, right? If you blow up a sphere. But how about, if the dots themselves also increase, right? That it is true, but the increasing of the dots is much smaller than the increasing of the distance between the 2 points. This is not because I put that in. That's because of mathematics. The further 2 points are away from each other, the more distance they will get as the sphere blows up. Now a point is made out of smaller points, but they are extremely close to each other, so that expansion is only very small. So ultimately, again, this will we do after break, but you put everything together, you will get 2 equations, the Friedman equations, and they relate the scale factor, if you will, the size of the universe, how far 2 points are away in the universe at any moment in time, and the curvature of the universe, which of these 3 possibilities, will relate it to the pressure and the density of the gas with which you describe the energy distribution in the universe. That's the whole plan. So during the break, just a second ago, I wrote down what we just put in words, but now in formulas. Here's the metric, Friedman-Robertson-Walker metric. Does it look somewhat familiar, maybe? So -1, there are some r squared, sine squared theta.
Yeah,
Schwarzschild.
No, wasn't it a different one?
The Schwarzschild contains an M. There's some mass in the middle. There's no masses here.
More like a spherical.
No, it's the normal radial one with just the factors multiplied.
Yes. If you would set k to 0 and you set a to 1, you would get back your Minkowski space-time in spherical coordinates. Well, I promise you that if you put k equal to 0, you would get back a flat space. Well, that is very true. Let's concentrate on that for just a second. Suppose that we look at the k is 0 situation. You would have this. Right? This is flat space. Well, it would be flat space if the a were all 1. Well, they're not all 1. They have the value a. So what we have here is a Minkowski space-time where the spatial directions, these 3, this is sine, the spatial directions come multiplied with an additional factor of a. So it's a number that tells spatial dimensions how big they are. This is why it's called the scale factor. It scales up the universe. If a were 1, you would have Minkowski space-time, period. You would have Minkowski space-time in spherical coordinates. If a, on the other hand, is 4, you would have still have a Minkowski space-time. It's just 4 times bigger. where things are 4 times further apart from each other. If you would make A time dependent, what you would have is a Minkowski spacetime on which all the spatial distances increase in time or decrease in time depending on what your value of A is. So this is called the scale factor. If you want, you can relate it back to this 4-dimensional sphere on which there is a 3-dimensional space and that's the radius of the sphere or something like that. I mean, it's related to each other. But let's fix on it in the following way. We have 2 points somewhere in the universe. Here's a point, here's a point. There's an amount of distance in between the 2 things. I wait 2 seconds. Then the number A has increased. So that means there's more meters between me and that thing over there, even though I haven't moved and that thing hasn't moved. It's space that has moved. And the movement of space in spatial direction is called A. That's what the scale factor does. Now, where did this come from? Well, everything that we've discussed conceptually, if you have only these 3 options to get the universe that is isotropic and homogeneous, and you write this down in mathematics, you will find that there's only 3 of these possibilities, and you can write all 3 of these possibilities in this particular form. And we put back the situation where it's not necessarily a flat space. Put the K thing back in. So this is not an additional assumption, this is just the mathematics of what we discussed before the break. Now if you want to know where this particular metric comes from, why it looks in this mathematical form, that's one of the exercises to prove that that is the case. So there you are. Question. This A, I say, is a scale factor. Again, it says something about what the distance is between any 2 points in space. Why is a thing only time dependent and not space dependent?
Because it is a property of the space itself.
But that's not per se an argument. I can have a Schwarzschild metric where things really look different at different positions in the space. Closer to the black hole, there's more time dilation than further away.
It's because the universe has to look the same everywhere in space, but not everywhere, the same everywhere in time.
Yes. Yes. The cosmological principle says it has to look the same in all directions, and this should hold everywhere. So that means whatever you write down for the metric, it should not be space dependent. Whatever comes out should be the same result anywhere in space. So A cannot be space dependent. It can be time dependent, because it relates back to our discussion before. The cosmological principle does not say that the universe should look the same at any moment in time. So it is allowed to depend on time. So the fact that this thing is only time dependent and not space dependent is, again, another way of putting the cosmological principle in. Now here it becomes a little bit more convoluted. Here's the expression for the energy momentum distribution if you assume that you can write everything as a gas. Where this comes from, again, this is Lagrange mechanics, and it's not particularly necessary for what we're going to do today, so you can take this as an assumption. Okay. If you want to know how this works, feel free to ask me at some point and I will explain it to you. You can also read it certainly in this book, not in this one. For us, it's just an assumption. You can write down the assumption that the energy is distributed through space as a gas. It boils down to this particular expression for this tensor here. So there's that. So this is putting everything in more mathematical terms. By the way, we have a metric. So that means we can calculate Christoffel symbols. We can calculate how things will move through that space. And yes, that is an exercise. So you can see if you have a space that is expanding, how will things move through that space? And maybe you can already think of an answer just by viewing a space that is increasing in time. If not, calculate the Christoffels, do the geodesics. It's going to be simple because look, there's so many beautiful zeros in there. And look that everything can only depend at most on time and on r and possibly theta. So there are not that many non-zero Christoffels. Yes?
But it's the choice of our, like if we say the universe is flat or spherical, so is that not going to change how things are going to move?
Yes.
Right?
Yes, because there is a k in the metric, so you can expect a k to be there in the Christoffel symbols, so you can expect a k to be there in your geodesic equations, so you can expect that things will move differently in a differently curved space-time. And again, that's an exercise to go through that to see what happens. Now, again, plug this into here, plug this into here, and you get out a relation between these two and these two. Yes.
I have a question.
Sure.
Like we said that we have like 3 different versions of how space can look like. Is that like, are they all equally, say, there's no one preferred towards the other? Or
No.
like
Not based on the cosmological principle. It's up to experiment to decide which of the 3 possible ones, if you will, which of the 3 possible Ks nature has chosen.
So the knowledge we have nowadays, we cannot distinguish between one
No,
of these.
the Friedman-Robertson-Walker matrix, just based on this principle alone, will not tell you which of the 3 Ks is the most likely one. It's up to experiment, because you calculate how things would move, you measure how things move, and then you calculate back which of the 3 Ks is
Can
the
you not
most.
see it by looking how galaxy moves
Yes.
through space? But
Yes,
Can
absolutely.
you not see then, okay, this galaxy moves like this towards another one, so it should be a spherical universe? also?
Yes, yes you can. But this is after the fact. After you've assumed K without a value, then go through the calculations and compare your results to experiment.
Okay.
You would be hard pressed to, just by looking at how universes move, galaxies move, immediately know what K is. So what people do, they assume one of the 3 Ks, go through the calculations, calculate the geodesics, compare to experiment, then tell you what K is. By the way, K is 0, as far as experiment tells us. So the universe, or nature has decided that a flat universe is the most likely one.
So we have a small preference.
Well, yes, I mean, again, all 3 possibilities are allowed by the cosmological principle, and nature cannot choose all 3 possibilities, has to choose one of them. And experiment tells us it's the K is 0 option.
But then would we even be able to tell the difference between the 3?
Yes.
As in, by observation, would we perceive all of them in the same way?
No, they would look very different. I can tell you more about this after we've done the Friedman equations, because this is where the K appears. But the short answer is yes, you can differentiate between the 3 by observation. Yes?
But so the value of K can change over time.
That is an assumption that you can make. That was your question too?
So basically, the shape of the universe can change
Yeah.
at some point.
Like as it expands, it can.
Wait, as it expands, it will look more flat. That is very true.
But
That's
is
not
it
quite.
possible for it to also change shape?
No, you're right. I mean, I understand the question. That you say, well, let's make this K itself time dependent, not space dependent, maybe because of the cosmological principle, but time dependent. The fun thing then to do is calculate the Riemann scalar. You might have forgotten this, but at some point I told you, when we were talking about geodesics and the geodesic equation, that I said, how can you tell if you are in a curved space? And I said, well, one thing you can do is take 2 geodesics and see if they close in on each other or not. And I said, a measure for this is exactly this thing. There's an equation that relates how 2 things that move in space-time close into each other or away from each other. That's this thing. If this thing is 0, then regardless of how difficult the metric might have looked, it was secretly Minkowski all along. Now what I can do, if I want to have a space-time, by the way, I don't know the answer to the question, so I'm thinking out loud now. If I want to check whether a space-time obeys the cosmological principle, what I should have is an R that doesn't have to be 0, but it's not allowed to be space-dependent, because otherwise things would have moved, 2 geodesics would have moved differently here than over there. So one thing we can do is take this metric, including the K that does depend on T, calculate the Riemann scalar, see if it is space dependent. If it is, then we're breaking the cosmological principle. Now, I know for a fact at the moment that this is not K dependent, then this thing will only be time dependent, which agrees with the cosmological principle. And I don't know what happens if it is T dependent. Unfortunately, it's not an exercise we can easily do because it takes forever to calculate these things. But it's a good question. I have a computer program that I wrote as a student to calculate these things. I should just plug it in just to see what happens. So short answer, I don't know. But I do know a criterion to determine whether that's true. So open-ended answer. Yes?
This is a bit of topic.
Okay.
How would this relate to wormholes?
It doesn't. There's no relationship.
Because it's like usually the way they used to visualize wormholes is like the universe is a flat sheet and you can like bend it
Well, yes. Okay. No, that is good. Sure. If you take but there's no wormholes in here. Okay.
I guess.
Okay, but if you, I mean, wormhole comes with its own metric. In fact, it's in not these two books, but the Hartle book. There's a wormhole metric exercise somewhere in chapter 7, I think, which you can just calculate through. Just calculate what the crystals are and see what happens and where you end up and such. But if they draw wormholes, they typically have indeed a sheet through which a tunnel goes to some other point or something like that, and that sheet itself, apart from the wormhole, is flat, right? And that sort of assumes that aside from the wormhole, they've chosen the K0 possibility. But remind yourself that all of this only holds the scales of about 100 megaparsecs. And if you go to a wormhole, then you will not see these effects. I mean, if you zoom in enough on any curved spacetime, it will look locally flat. Now, all of this holds for extremely large distances. So if you zoom in on a wormhole, the rest of the space will look locally flat to you. So if you see a picture in a book that has a wormhole in a flat space-time, that's not that they assume that K is 0, they just assume that they've zoomed in enough that it looks flat locally.
Do we assume that it has an infinitely small size, so that it's just a local thing, or can it have an area?
It depends on this sort of, it's a little bit semantics. What do you mean by the size of a wormhole?
Yeah.
I mean, do you mean the radius of the throat? Something like that?
Like mathematically seen, do you consider it as a singularity?
No, you don't. No. There will be a tunnel. I propose to put these things together, skip the mathematical steps, not because it's not particularly difficult, it just takes forever. I just give you the Friedman equations that comes out. So we're going to combine this. Here are Friedmans. There's 2 of them. Why 2? Well, because, as I told you before, this is 10 coupled differential equations for the 10 possible values for these things. Right? What this thing tells you, generally speaking, is what the 10 elements are of your metric tensor. There's 16 of them. There's 16 numbers in there, but because it's symmetric, that means you only end up with 10 independent ones. So, principally speaking, this will give you 10 different numbers. But because it's a diagonal matrix, it has reduced to 4. And if you think about it a little bit more, you would expect only 2 numbers to come out. Can you think of why that is? So there's 10 numbers because of the symmetry of the metric. It reduces to 4 because our metric happens to be diagonalized. And now I say, well, those 4 numbers you can reduce even further to 2.
One of the reasons being one of the metric entries is just a constant.
No, not necessarily, no. It's again a cosmological principle, but rearing his head in yet another way. Is there any difference between going into x direction and y direction, say? Should hold wherever you go, right? So that means that whatever comes out for what happens if you travel through space, there's 3 dimensions, but these 3 dimensions should give you the same answer. So of these 4 numbers, 3 of them say something about space, because the cosmological principle really should give you the same equation. It's hard to see because we just happen to have chosen spherical coordinates, which sort of messes up the look of the symmetry, but it is symmetric. It looks the same in all directions. So that means that ultimately you only get 2 equations out. One, if you will, that says something about what happens if you travel through time, and one of them if you happen through one of the space dimensions. And then the other 2 space dimensions obey the same law. Here are the equations. A dot means derivative with respect to time. This is the first Friedman equation. We just first write them down and then see if we can see some properties of these things. That's the first. Here's the second. Double dot, 2 derivatives with respect to time, equals minus 4 pi g over 3c squared rho plus 3 times p. There we are. We have now reduced relativistic cosmology to something very beautiful and very simple. Because somebody just has to tell you, well, it's mathematically difficult, but it's conceptually simple. Somebody tells you what the pressure and the density are of the gas, which with the universe is filled. You put them in here. So if somebody tells you what this number or this function is, or this number and this one, and your assumption of the curvature of the universe, you can solve this and get A as a function of time. And because A is a function of time, says something about whether 2 points in space are moving away from each other, this is when A is increasing, or close in on each other, this is when A is decreasing in time. These two tell you for any given amount of energy and pressure in the universe, how the universe will evolve through time, or what it has done in the past. These two are the basics of cosmology. Of course, there's much more, right, because you have to put in temperature and all these extra effects. But this really is the basis. If you want to know how the universe is expanding, given the amount of energy in there, solve these equations.
So the acceleration of the expansion is also changing?
Yes.
Okay.
That's what you can see here, right? Because this is the acceleration of the expansion. It's good. Let's go to the interpretation of these equations. One of them is A dot, first derivative of the scale factor, just tells you how fast the universe is expanding. If this is a positive number, expanding universe, things go bigger. In very much the same way, if it is smaller than 0, you have an what's it called? Contracting. Contracting universe. If A dot is 0, you have a static universe. Its size that does not change. Yes?
Can you tell us more or less what would happen if we would live in a contracting universe?
That any 2 points in space, if you wait long enough, will get sucked into each other.
But in terms of time and stuff like this, would it behave differently?
What do you mean in terms of time?
I don't know if it's gonna change. I don't know. I haven't really thought about it, but like except from like I said, 2 points getting closer and closer.
Mm-hmm.
They change something, like something mind-blowing.
Literally just means this. You have 2 points in space, any 2 points. Let's take you and me. Well, we're not at the scale 100 megaparsecs, but suppose that we were. That even if you and I are not moving ourselves, the space in between us will get shorter and shorter. That means that you and I, as time goes on, will get closer and closer to each other. It's not because your gravity and my gravity are interacting with each other, it's because the underlying space does it for us. Now, if that's the case for not just you and me, but for any two people in this, over here, everything will, at some point, clump together. There was once a viable theory of cosmology, it's called Big Crunch, where if you wait long enough, everything will get sucked back to the original starting point, namely Big Bang or so. So we have an opposite Big Bang. Now we will see in a second that this is not possible anymore based on our observations. Let's go through the list a little bit more. There's A dot dot, which says not just if the universe is expanding, but if it's accelerating or not. Now what can you tell immediately from the second Friedmann equation? It comes with its own minus sign. A itself is always a positive number. It's the distance between 2 points.
It's always going to be negative.
Yes, because it's hard to have a gas with a negative pressure or density. So these numbers are always positive. If this is always positive, then with this minus sign, A dot dot is negative. So you expect that the expansion of the universe, A dot, is itself decreasing. So it might be expanding, A dot is bigger than 0, but the expansion is slowing down. This is what the Friedman equations a priori will tell you, just by looking at this. Yes?
But then is there a reason why the minus sign is there?
No, it really just comes out of the mathematics. There is something to say about this, and that is, well, because gravity is always attractive. It tries to pull things together. It doesn't try to push things away. Then, of course, there's a statement, what about dark energy? We'll get to that in a second. Yes?
But we know from experiments that we live in an expanding universe, which is expanding faster and faster.
Yes.
So why are we regarding the A values, A dot values, which are negatives? Because we know that experimentally it's not.
I agree. So that means that there's either something wrong with the Friedman equations, or there's something, so the form of the equations itself, including the minus sign, and not a mathematical mistake, but there's really something wrong with our understanding of general relativity or such.
Okay.
Or, one other possibility is that what we use for P and rho is not entirely correct.
Okay.
If you play around with your P and rho, you can make a situation where this thing itself is negative, which cancels this negative, and then you get an accelerating, expanding universe. By the way, this assumption is called dark energy.
Well, we talk about the dark energy, but what about dark matter?
It's not in here, not per se. Dark matter behaves, as far as gravity is concerned, as any other matter.
Yeah.
So that means that if you're going to write down your rho, your density of dark matter, and your pressure of dark matter, you can use the same assumption as any normal matter.
Okay.
The only thing dark about dark matter is that it doesn't behave electromagnetically.
Okay. But that should have some consequences now.
Yes, for the amount that you put in, but not for the actual physics. The dark energy really is a different kind of thing altogether. Dark matter is unknown, we don't know what it is, but we do know that what it does is the same as normal matter. Dark energy, we don't know what it is, and it behaves differently from everything else. So dark energy really is the bigger mystery. Hey, let's put some more conclusions in. There was a question before about the fate of the universe. What will happen if you wait long enough? And then I said, well, it is related ultimately to this K over here. We can draw that conclusion immediately without even going as far as showing what the full solutions of these things are. Do you agree with me that the biggest the universe can get is when A has its biggest value? No matter what the number is. If A has the biggest value, then you have the biggest universe. A is the distance between 2 points, or is a measure of the distance between 2 points. If that gets its biggest value, that's the biggest universe. Just from your everyday first year calculus. A dot 0.
Yeah.
You get your biggest universe at the moment that A dot is 0. So let's put that in. Let's see what happens, what biggest universe you would get based on the first Friedman equation. And biggest universe is mathematically the same thing as saying A dot is 0. Because this is the biggest value that you will get for A is when its derivative is 0. The biggest universe that is possible. Indeed, A dot is 0. Put that into the first Friedman equation. What do you get?
So you just get 0 equals
Right inside, right inside.
Yes. You will get this,
Yeah.
right?
Yeah.
That's the biggest universe you can get. You tell me, rho, positive number, negative number, what is it? Positive, right? It's a density, amount of energy per volume. Okay. If this has to be a positive number, what does it tell you about K? Also has to be positive. Yes?
Just like a random thought that
Okay.
because it's expanding, like that, so we're assuming that it eventually like reaches a limit and it just stops expanding right there, and that's when A dot is 0.
Yes.
So okay.
It is like throwing something upward in normal gravity. The highest point it will reach when its velocity is 0. That's the moment when it stops going upward and starts going downward. And that's what we do here. So the biggest universe, A dot is 0, put it into reverse Friedman, it tells you, well, then this has to hold. But since you know that the rho has to be a positive number, just by its physical definition, it's an energy divided by volume, then this tells you, well, then K has to be 0 as well. It has to be positive as well.
But A is infinitely big at that point.
That's not so much an issue per se. By the way, I never said it was infinite. It could also be just some big number. I'm just saying it's a big number, the biggest that it can get. It's not the biggest number that exists. It's just the biggest that itself can get. So don't assume that this is infinite per se. This is positive. K has to be positive in order to make this happen. Now, which of the three universes had a positive K? The spherical one.
But you said that was just convention, right?
No, the fact that it is plus 1. Not that it's plus.
Oh, okay. Okay.
Maybe you could also choose it as plus 15, but people chose plus 1. Just the fact that it's positive that's not convention.
That's not convention.
No.
Okay. Yeah.
What number it is positive, that is convention. They chose 1. So we have something interesting here. We see that the only way to get a biggest universe is when you live in a spherical universe. The other options, flat universe says this is 0, which doesn't agree with this. Or a hyperbolic universe, which makes this negative, also doesn't agree with this. Now, if you have an expanding universe, but the universe is either flat or hyperbolical, and it says you can never fulfill this condition, that's another way of saying it will never get to its highest point. It will always expand forever. It will never stop expanding. So just without even solving these equations, you can immediately tell what kind of curvature will give you what future in the universe. Again, you do the measurements and you will find K, as far as we can measure, is close to 0 with some percentage experimental error. So we know that whatever the universe does, it will never contract again. It will never stop its expansion and then start going backward, even regardless of its accelerated expansion that we measure now. Isn't that beautiful? You can just conclude that without even going through the full mathematics. One more. There's something, oh, so yes.
It's maybe somewhat of a trivial question, but
Okay.
do we have any idea or any notion about what the universe is expanding into? Because if it is expanding, there needs to be, at least in my classical conception, some kind of space
Yes.
where it can go.
Okay, yeah, that is indeed, there's your answer. It is a classical conception. What I said here is the universe is growing bigger, and what I mean by this is that any 2 points in the universe will lie further and further away from each other. You can achieve that even if the universe itself is already infinitely big. It's just, it gets more big. And one metaphor that I typically use for a question like this is a very good question, because what you're really asking is, what do we mean by the expansion of the universe? And the way that you can describe this, or make the subtlety clear, hopefully, is as follows. That if I want to expand the space in this lecture room, one thing I can do is just move out the walls, right? Make sure that the walls, all of them, get a meter apart from each other. If this is your concept of expansion of the universe, that the boundary gets further and further away from stuff, then it's a very good question, yes, but what is the boundary expanding into? Okay, then your question is very valid. But here's a second way of expanding a universe. Suppose that you already are in a room that has no walls whatsoever. It's already infinitely big. How can you then tell that it's expanding even bigger? Well, it doesn't help to look at the walls, because there are none. What you can do is look at 2 points and see if they are moving out away from each other. In that context, and that's the context how we mean it here, there is no space in which things are moving away. There's no thing in which the universe is expanding. If you will, it's an intrinsic measure of expansion. 2 points within the space get further apart. It's not that the boundary of this space gets further apart. Yes?
further apart still?
Well, the question that depends, is there a boundary to talk about? As far as we can tell, there isn't. Yes, please. Or
Mine is going to be quick, I think.
Okay.
Has anyone ever thought about like having the boundaries like a wall fixed and everything is just getting smaller and smaller? And so it appears to be further apart?
no, at the moment that you and I get closer and closer to each other, it might look, just by looking at the walls, as if the walls are being further and further away from each other, right? But I would be able to tell from you and me that we are really contracting. Your measurements would look very different in a universe where we are fixed and the walls are expanding, or the walls are fixed and we are contracting. It would look different because you and I would look different with regards to each other. Even though as far as the walls are concerned, things will look the same.
I don't know, like maybe I'm not understanding your answer, but imagine here in the room you put like two oranges, right?
Yes.
And instead of moving those oranges into space, you just make them shrink, basically.
Ah, okay.
And so the distance between them, relatively speaking, increases.
Okay.
Like everything.
No, I understand. Okay, I was assuming in our situation where I said you and I would be able to tell that we're closer to each other, that would not hold anymore if, as much as we are closing into each other, we're also shrinking. Because that would look as if we were both standing still. And I think it might look even, it might be that your situation where things shrink actually does look like an expanding universe, even though it's not expanding. So I think the answer is, I say a very careful yes, I say to your answer.
Okay.
There's two more points I want to make, so yes.
Instead of contradiction, you said that since we measured k is like slightly bigger than 0, so it is infinitely expanding.
Yes.
But should not at some point be like because first there was like the Big Bang, everything exploded and went in our direction. But at some point should not the gravity take overhand of this expansion and take everything back, because we said that the reaching of the gravitation is like infinitely.
No, that is okay. That is a very good question. I say the universe is expanding forever. This has nothing to do with the accelerated expansion. Just based on the frequent equations, you say things are expanding, and we see that if it's not a spherical universe, it will keep on expanding because it will never reach its biggest value. Yes. So
if it is spherical.
Yes, if it is expanding. Yes. And then what was your question?
That at some point the gravitation should take over.
Yeah. No, that's a very good question. That's very good. Okay, listen. I love this question. It's such a good question. Universe is expanding. We see that blah blah blah. Spherical universe. At some point it will stop. Let's assume it's not spherical universe, hyperbolic or flat. Well, let's just take flat because we know from experiment that it's flat. Okay. Then the universe is expanding forever. And then you would say, but at some point gravity will de-accelerate things, right? And if gravity is always working, even at some point, if you wait infinitely long, it will have enough hold to slow down the expansion or even stop it altogether. That is very true, but you also have to keep in mind that the amount of gravity decreases by bigger distance because it goes 1 over r squared. So there's two effects here. The universe itself is expanding, then gravity tries to grab hold and tries to put everything together, but what if it's expanding more, then gravity can catch up with it.
So okay, we never.
Yes.
Oh, okay.
And in fact, if you put that into mathematics, then there's a difference between k is 0 and k is minus 1. Both of them are infinitely expanding. If you go through the mathematics, you will find that the flat universe expands a little bit slower than a hyperbolic universe, which allows gravity to grab hold of things and try to slow down. And you will find in a flat universe, if you wait long enough, that the amount of expansion, that a dot, will go to 0 at infinity. So at some point gravity will have slowed down everything, but it takes an infinite amount of time. Hyperbolic universe, which expands a little bit quicker than a flat universe, even if you wait long enough, then still the expansion rate will not have gone to 0. So will gravity at some point grab hold of things and start putting things back together? Well, the best it can do is in a flat universe in which it takes an infinite amount of time, and it's an hyperbolic universe, it never happens to begin with. And that's because of the 1/r squared decrease of gravity.
And in the spherical one?
Then it will, because that's exactly what it says here. At this moment is when the universe, the gravity, has made the universe come to a standstill. And then it starts grabbing all things and starts pushing everything together. You get a big contraction.
But here K has to be positive.
For a spherical universe, yes.
So if K is positive, it's
So this
okay.
would result in
Okay,
a big
okay.
crunch if that were the case.
Yes. Because this is the biggest amount that it gets, but just like if you throw something upward in gravity, its highest point will be when its velocity is 0. It will not stay 0, it will not stay floating there. Gravity will accelerate it inward. Just here. This is just the biggest value for K is positive for a spherical universe. If you wait even longer, it will start contracting again. And at some point this was a viable theory before we knew that K is 0. So we don't have to worry about big crunches anymore. Yes?
Is it correct to say that the expansion of the universe is invariant? So like, no matter your position, your velocity, your reference frame, you'll always observe the same amount of expansion. I don't know if invariant is the right word here. But
It's
feel
not.
like
I do understand what you mean, but invariance is indeed not the right word. So that's the answer. Is there room for 2 more points? One of them, what I wanted to make was this number, h dot over a. It's typically called the Hubble constant. H naught. Then you might immediately think, wait a minute, why is it called a constant if it consists of a time-dependent function? That's because it's not a constant. Historically, when Hubble found a law that says something about the expansion of the universe, as far as his measurement is concerned, h naught was indeed a constant. Later on we found that it isn't, but it's still named the Hubble constant. It's not a constant, it's the best I can say. It's a time-dependent function. Here's an interesting observation. Let's see if you can put this thing together. If I do this, I have this number. Yes, the number changes every day, but suppose that I take its measurement of today. What is the value of the Hubble constant right now? And I take 1 over that number, 1 over h0. It's the age of the universe. Can you see why?
Unit-wise, yes, because you have an acceleration. Velocity over distance.
Yes.
So if you get distance over velocity, you get time back.
Okay, so it is a time. 1 over h naught is a time. So that's very true. But why is it the age of the universe?
What was the definition of A again?
And how far apart 2 points are at this moment in time.
Any 2 points?
Any 2 points.
So it can also, so it can be 2 points, and oh no, you don't have counts over edge of the universe. But if you would,
Some far away point, okay?
yeah, so like really far away points. If you take those 2 points, yeah, oh my god, I can't explain it. I have it in my head somewhere.
Okay.
But no, never mind.
Suppose that I tell you I have a car and it left home, and it's moved 20 kilometers. And suppose that I say that it moved with 40 kilometers an hour. Can you calculate back how long it has been driving? You can, right? Now I have 2 cars here. The 2 cars are 2 points in space-time. They're not moving on the space-time, it's space-time itself that moves. But I have 2 points in space, and I tell you how fast they're moving away from each other, that's a dot. And I also tell you how far away they are from each other now, that's a. Can you then calculate back how long ago they were squeezed on top of each other?
Yeah.
which we would call the Big Bang, because that's the
Yeah.
moment when everything was back.
Yeah. Yeah, that's good.
That's this thing.
That's so cool. Very great.
But that's good. That means if somebody measures this thing, h naught, you take the inverse of that number, you get the age of the universe. Not quite though. It's bigger or. Can you understand why that is?
So that has to do with the fact that it's not constant.
Yes, because the car has been slowing down since the beginning of the universe. Right. This second Friedman equation.
Slowing down.
Yes.
Remember? There's a minus sign in that equation.
Oh yeah. Yeah. Oh yeah. Sure.
Yes.
Yeah.
So the number you will get out if you calculate this is assuming that it's always driven with the velocity that it had.
Yeah.
It hasn't. So you get a limit on the number. Now the fun thing is, you can measure this number very easily, in fact. The only thing you have to do is take two current things in space. This is what Hubble did in 1929. He took a number of galaxies, and he saw how far away they were moving from each other. He measured h dot. So you can quote unquote easily calculate what this number is, and our measurements are getting a lot better still and still. In fact, the best numbers that we have right now is that h naught in, don't ask me why, but this is the units that they put this in, is about 70 kilometers per second per it's either megaparsec or parsec, I forget which one it is. It's some number that we know.
These measurements were done with the gravitational waves.
That's how we do it now, yes. But you can also just do it by looking at the light that comes from galaxies. You'll get a similar number. I mean, there's about 10% difference or 7% difference or so. The hope is that within 10 years of gravitational wave detections, we can get this number down to 1%, which means that you get the age of the universe. With this number plugged in, this number comes to about 15 billion years. And if you do it very carefully, including how h naught have changed through time, that means solving these equations, you will get a better number, and that's the famous 13.8 billion years. That's the moment that if this long ago the cars all started from the same point, which is the Big Bang. All these things you can calculate even without doing the actual equations, just by looking at the mathematical structure of these things. Now, Arthur, you had a question, I think.
Yeah, I was just thinking, like, they had to find. So you said they kind of took two galaxies.
Yes.
Do they have to be in the same like inertial frame, or because they're still moving to this galaxy, right?
Yes.
So I was just wondering, do they have to take like a specific case where they're behaving similarly to be able to calculate that, or you can use also?
Well, they're both in inertial frames. Well, it's hard to put inertial frames in the right context here because of the. Typically, you use inertial frame and non-inertial frame at the moment that you have differences in space where they are. And right now, because of the cosmological principle, it doesn't really matter where they are. It's hard to put it in those terms, but yes, you can in principle take any two galaxies. All right. Well, you can imagine what the exercise is going to be. One of them is see if you can find how this works. That's the big exercise. The smaller exercises are simply this. First of all, calculate the crystals. See how things would move in that space. That's one. And secondly, there's a number of cases where I just give you rho and p, and you tell me how the universe has evolved. That's the idea. But this is not for now. This is the conceptual understanding of what we have here. So there was two final points. I just made one. That's this one. Final one was, yes, the dark energy thing. This is a minus sign, so it says things cannot accelerate. But they can, though, if you make this thing itself a negative number. How do you make that a negative number? Just make sure that rho is a smaller number than 3 times p. then minus 3 times 3, excuse me. Agreed? Now there's many ways that you can do this, but what you can do is say, well, let's assume that rho is minus p. I'm making a mistake here somewhere. It's probably 1/3 or something. Let's see, this has to be negative. Rho plus 3p has to be the negative number, so rho has to be smaller than 3 times p. Rho smaller than 3 times c is minus p. Messing up here something. Well, let me think about it in the break. The long story short is that this particular rho and p relationship will make the universe expand.
Why is there a mistake?
Sorry?
Because if rho is minus p, then minus p is smaller than minus 3p. So, then.
Oh, you're right. No, you're right. Yes, there is no mistake. No, you're right.
Yeah.
So you see that this obeys this general condition, yes?
Yeah.
So this is one particular case where this holds. Now, yeah, you're right. Thank you. Just confusing myself for a second.
More negative pressure.
Yeah, that's strange, because what we have now is that you can make the universe expand faster and faster as long as this relation holds. For instance, by doing it in this way. But then you would have a situation where either the pressure is negative or the density is negative. And normal matter does not have negative pressure or negative energy density. So you have to have some very special new sort of stuff to make this work. Now, we don't know what it is. This is why we call it dark energy. This is the assumption. That is this option. If you plug this into the Friedmann equations, you will have an accelerating universe, but even more. This is one of the exercises. You will find that your A, right, you can then solve your equations and find what A is as a function of time. Under this condition, you will get that A is exponential. It's an exercise to go from here in the Friedmann equations to there. Is an exercise you can do. That means that if you have dark energy, or whatever stuff that obeys this relationship, you have a universe that expands exponentially. It really goes faster. Nobody knows what that stuff is. And an option is, well, this simply does not exist. It's these equations that are wrong. Again, nobody knows. Okay, whew. Okay, that's way enough for now. Any questions conceptually? The rest is just putting in the mathematics. No? All right. Let's have a break, a presentation afterwards. I think I solved it.